So let's start practicing electron configuration. First, I'm going to teach you how to do it based on the periodic table. You're going to use the periodic table to identify your electron configuration. There are other patterns out there, okay, other recommendations on what to use, but I find that almost all of my students can do it very well, very simplistically, straight from the periodic table. You already have one anyway, so it's less things to memorize. So please use this. You're going to need to be able to identify the S, P, D, and F blocks on the table, and I will show you what those are in a minute. You also need to remember, though, the blocks start with very specific things. So the S block starts with one S. The P block starts with two P. I'm having the worst luck trying to write right here. 2P. The D block starts with 3D, and the F block starts with 4F. You're going to begin with the first period, which is the first element on the table, hydrogen, and you're going to count across that period. You're going to proceed horizontally across the periodic table, counting the electrons in the SPD and F blocks until you reach the element of interest. So, just generally speaking, here's where your periodic table is constructed. Okay, your S block is your first block. So your S block is over here, and helium does fit in right here when it comes to electron configuration. Okay, as the helium is over on the other side for the P blocks, it's a noble gas, but for electron configuration, it sits right here next to hydrogen. Your P block, you can see here. So your S block contains your alkali metals and your alkaline earth metals. Your P block is your other main group elements, including your noble gases, your halogens, oxygen's family, nitrogen's family, carbon's family, boron's family, all of that. Your D block is your transition metals. And your F block is your lanthanide and actinide series that we kind of forget is down there until we need those elements. Okay? So, three rules for determining the ground state electric configuration is the Aufbau principle. This is the idea of building up. Okay? What this means is that we always have to fill those lower energy levels before we can fill the higher energy levels. If you are building a house, you have to put the bricks at the bottom before you put the bricks on the roof. It's just the way life works. You have to build up. Lower energy first, filled up before you fill up the higher ones. Build it up. We've got the Pauli Exclusion Principle. The Pauli Exclusion Principle says you can have a maximum of 2 electrons per orbital as long as they have opposite spin. That's the easy way of saying it. The real way of saying it is that no 2 electrons in an atom can have the same 4 quantum numbers. That's the more correct way of saying it. Basically, no 2 electrons can have the exact same space. So what this means is pictured here. In the 1s electrons are drawn correctly. They're spin opposite of one another. But the 2s, this cannot happen. I cannot have 2 electrons that are both spin up. If one is spin up, the other has to be spin down. They cannot have the exact same 4 quantum numbers. They can't have the same spin. And then Hund's rule is the parallel before paired idea. The better way of saying that is when filling degenerate orbitals. Degenerate again means equal in energy. The electrons occupy these orbitals singly, one at a time, with parallel spin before pairing up. And we can see that in the pictures here. Basically, what this is saying is that this first system will not happen. The electrons want to go parallel before they pair up. You're getting on a school bus, you want to sit individually before you have to pair up with everyone else. Okay? Maybe not on a school bus, maybe you like your friends. But if you're getting on a city bus and you don't know people, you're going to want to sit in your own seat before you have to sit next to somebody. We've got ground state and excited state. Ground state is just the lowest energy state, where that species exists in its lowest energy state. Excited state is any other state than your ground state. The electron has been promoted to a higher energy state. And again, degenerate, I said, means equal in energy. And so like our s orbitals only have one orbital shape. So they're non-degenerate, it only has one orbital. But p's have three. Their m sub l's are negative 1, 0, and 1. Those are all equivalent in energy. My d orbitals have 5 m sub l values, negative 2, negative 1, 0, plus 1, plus 2. They are all equivalent in energy. We've also got node, shell, and subshell. A node, again, is that region in space with zero probability of finding the electron. Your wave function is equal to 0. The electron cannot reside there. It can flip between there, but it can't stay there. The shell is the energy level you're in. So like your n equals 1, your n equals 2, your n equals 3, whatever it may be. You can see here, our shell described here is the n equals 2 energy shell. Subshell is your energy subshell. So your subshells here are your s orbitals, your p orbitals. They're subshells within that overall energy level. We will be flipping back and forth to periodic table, so we've got one in here so that we can see it and we can use it as needed. Okay, so give the 4 quantum numbers and electron configurations for the following species. Let's go through it. First up, we have hydrogen. If I look at hydrogen, I'm going to find hydrogen on the periodic table. So first goal, find it on the periodic table. We've got hydrogen. It's the very first element that we have. Okay. So what we want to do is this is always where we're going to start to. You're always going to start with hydrogen. So it's kind of convenient. We are in the n equals 1 energy level, and we're in the s block because we have memorized s block, p block, d block, f block. Again, s block, p block, d block, and f block. Okay. So we have memorized where we are at here. We're in the, we've got the block we're in. We know where we're at. We start off at hydrogen and we've already reached the element we're interested in. That's great. That makes my life easier. That means I don't have to quote unquote go further to reach it. I've already got there. What I do is I describe where that electron is. I'm in the n equals 1 energy shell. I'm in the s block, and I have counted one space, hence one electron, to reach that space. Hydrogen 1s1 is the electron configuration for it. By saying 1s1, I'm saying first energy level, s block, and one space here. I have described the electron configuration where the electron resides for hydrogen. Now the 4 quantum numbers for this, again, quantum numbers are n, l, m sub l, and m sub s. N is your energy level. We just told you we're in the first energy level. L is the type of orbital shape you're in. We're in the s orbitals, and s always equals 0 for L. So s, L equals 0, p, L equals 1, d, L equals 2, and f, L equals 3. M sub L is equal to negative L through 0 to positive L. My M sub L value is my L value is 0, so my M sub L value can only be 0. That's describing the type of orbital I'm in. So for 1s, I only have one type of orbital, okay? And I have one electron in here, and it is spin up. So we say that that is positive 1/2 because it's spin up. We assume the first electron going in is spin up, the second electron going in is spin down. This diagram that I just drew over here, this one here, is called your atomic orbital. And so this is like your energy scale here, and it's showing where the electrons reside comparatively. So for hydrogen, 1s1 is the electron configuration, and its quantum numbers would be 1, 0, 0, and plus 1/2. Let's look at helium. Again, I told you guys that helium fits right here when it comes to electron configuration. So I'm still in the n equals 1 energy level. I'm still in the s block, but now I've counted 1, 2 spaces. Helium has 2 electrons in a neutral species. So I'm still in the 1, first energy level, still in the s block, but now I've got 2 electrons to account for. So I'm going to do the electron configuration for both quantum numbers here, or both electrons here. So the first electron versus the second electron. N, L, M sub L, and M sub S. So for hydrogen, we had this. For helium, I have 1 and 2 electrons. This is my first electron added in. This is my second. By convention, we always assume the first electron added in is spin up. The second electron added into that same orbital is spin down. So I'm going to say my n value here is 1 for both electrons because they're both in a 1s orbital. My L value is 0 for both because they're both in an L or an S-shaped orbital, so L equals 0. My M sub S, also 0 for both of them because they're both in an S orbital. It only has one shape. But my M sub S, the first electron in was plus 1/2, so like hydrogen had, but my second electron in is minus 1/2. This is emphasizing that idea that no two electrons within one atom can have the same 4 quantum numbers. They're the same through the N, L, and M sub L, but they're differing in that M sub S value. You will never have 2 electrons in the same atom with the exact same 4 quantum numbers because this is what distinguishes them from one another. Let's look at lithium. Okay, I see lithium is here on my table. So what I do always is I start counting at the very top. I count 1, I'm in the 1s orbitals, and I've counted 1, 2 spaces, but I haven't reached helium yet. But I'm going to write that down before I forget, okay? So 1s2, but I haven't reached lithium yet. I go across the table and there's nothing else there because again, helium is over here. Helium is on the other side of the table for electric configuration only. So I go across the table and I don't hit any other elements. So now I'm going on to the second energy level. I'm in the second energy level. I'm back in the S block now, and I one space and I've counted lithium. So 2 for second energy level, S for S block, and 1 for the 1 electron in that species. 1s2, 2s1 is the electron configuration for lithium. Now I'm going to do the quantum numbers, but for these last 4 elements, I'm only going to do it for the last electron added, just because I don't need to do it for all 3 of them, or in the case of carbon, all 6 of them. My N value, my L value, my M sub L, and my M sub S. So the last electron added in is right here. And again, if we're doing it by, sometimes it's easier to see it through the atomic orbitals, which is what this description over here. I filled my 1s, now I'm going into my 2s, and I've got 1 electron there. So this is what lithium looks like with its 3 electrons. My N value is now 2 because I'm in the second energy level. My L value is still 0 because I'm still in an s orbital. My M sub L value is still 0 because I'm still in an s orbital. And my M sub S value is now plus 1/2 because I'm back to being electron spin up for the electron that was just added. Let's look at beryllium. Back up to our periodic table. Beryllium is right next to lithium. So beryllium, I start here. I've got 1s1, 1s2, haven't reached it yet. 2s1, 2s2. Now I've reached beryllium. So I get 1s1, or sorry, 1s2, 2s2 for my electron configuration. Now, if I want to look at my quantum numbers here, N, L, M sub L, and M sub S, this is the same as adding my second electron here into my 2s. I've got to fill that. That's that build-up principle, okay? I have to fill that. That's the Aufbau principle before I can go to a higher energy level. This is all for ground state electrons. My last electron added in is this electron right here. So my N value is 2. My L value is 0 because I'm still in an s orbital. My M sub S is 0 because I'm still in an s orbital. And my M sub S is minus 1/2 because I am now spin down. Back to the table for boron. I start off at the beginning. 1s1, 1s2. Haven't reached it yet. 2s1, 2s2. Haven't reached it. Now I go across the table, and now I hit the p block. First electron in that p block, and I have reached boron. That is called your 2p's. Again, this starts at 1s, this starts at 2p, this starts at 3d, and this starts at 4f. P's are kind of easy because it matches the 2's, but the 3's and the 3d and the 4f do not match nicely, so you got to remember that. And it's definitely not going to scribble away at this point. Okay. So I have 1s2, 2s2, 2p1. So when I'm looking at my atomic orbitals here, I'm now into my 2p's, and my 2p's have 3 shapes, described as -1, 0, and +1 by my m sub l values, and I have put 1 electron there. So I'm going to move some things around on the screen. So we can fit this in. But my quantum numbers here, n, again, I'm describing this last electron added in. So now I'm describing this electron. N is equal to 2 because I'm in the second energy level. M sub L is equal to -1 when, or sorry, L value first before M sub L. L value is equal to 1 because I'm in a p orbital. And again, L equals 1 for p's. My M sub L value could be anywhere from -1, 0 to +1. By the convention, the first electron we fill, or the first orbital we fill in is called -1. And then my electron is spin up. So my M sub S is +1/2 because it is spin up. And if I look at carbon, carbon is one space past boron. So 1s1, 1s2, my S's are filled. 2s1, 2s2, S's are filled. I haven't reached it yet. I go to my 2p block, 2p1, 2p2. So 1s2, 2s2, 2p2. Now I'm going to add an extra electron in here, but it's going to go parallel before paired. So it's going to go into the orbital next to it. It's not going to go into the -1. It's going to go into the 0 for the M sub L value because they're going to parallel up before they pair up. They do repel each other and they don't want to be next to each other if they don't have to be. So, but now I'm going to talk about describing this electron in. So my N value is still 2. My L value is still 1. So I'm still in my p orbitals. I'm still in my 2p orbitals. But now my M sub L value is 0. And my M sub S still spin up is +1/2. So notice here, these two species differ in their M sub Ls. So because carbon has the same amount of electrons as boron plus 1 more, carbon has that electron that boron has. But these two electrons of carbon would differ in the M sub L values because they're in a different suborbital. So just a diagram showing the orbital filling. You can see here, 1s, 2s to 2p, 3s to 3p, 4s, 3d, 4p, 5s, 4d, 5p. Again, the PR table does this for you as well, but some people like seeing the orbital diagrams this way as well. And then kind of just showing you again, just going across the table that way. Let's just make it very, very obvious how they're filled when we go through it. So we always start here. Helium does hang out right here. But we're going to fill this going across. So 1s first, helium's on the other side. Then on, so 1s first, then on to our second energy level, 2s, and then our 2p's. On to our third energy level, 3s, then our 3p's. On to our fourth energy level, 4s. Do not forget that these are called your 3d, 4d, 5d, 6d. I need to find a color that you guys can see on there. So I'm going to write them really slow. 4d, 5d, 60, 70, or 3, 4, I can count. 3D, 4D, that's what I'm trying to do, 5D, 6D, and then 4F and 5F are down here. So as you're counting across, your 4S's go into your 3Ds, then you go back to your 4Ps. 5S's to 4Ds, back to 5P. 6S's, 5Ds, back to 6Ps, 7 S's. Also, the other tricky part in here, it's hard to see because I just covered it up. But if we look inside of here, we see here we're flipping between two numbers. If you look at the actual table, lanthanide and actinide actually fit in right here. Okay, they are actually part of that block right there. But then you have your F block that fits in as well. So the moment you get down into here, your 6F, 5D, you then fill 4F, then you finish filling the 5D. So it actually looks a little weird when you're filling them, but it goes like 6S2, 5D1, 4F14, and then you finish filling the your 5Ds. So like if I have a species, let's say I have tungsten right here, we will do tungsten a little bit. Actually, tungsten's one of the ones that looks a little funky, so let's do a different one in here. I can't see what's under here. Let's do ruthenium, 75. So like that would be, we would do a shorthand to get to there, and I'll teach you the shorthand in a minute. But you got xenon, 6S2, and then we would have our Ds, 5D5, 4F14. So the 4F14s will fill even though the 5Ds aren't filled, because again, if you look at the numbers here, it fits in perfectly in this space right here. We see 56 jumping to 71, 88 jumping to 103, and down here we've got your 57 through 70 and your 89 to 102. So that's how they're filling here though. And you can kind of see that here as well. So we've got, you know, your 6S, your 4F, your 5D, 6P. So in summary, your N value is your principal quantum number. That's your energy level. L is telling you the shape. M sub L is telling you the orientation in space. So like px, py, pz, dxy, dxz, dyz, dx squared, y squared, dz squared. You don't have to know the shape for F's. You do have to know them for the S, P, and D. And S only has one shape, it's just a sphere. And then your M sub S, that should be an M in front of there. M sub S is plus or minus 1/2. So let's work a couple examples. Write the complete electron configuration of titanium. So finding titanium on your table, go ahead and pull out a periodic table to do this, okay? So titanium, Ti, start counting across that table. Complete configuration means you write everything down. We will do an abbreviated, which a lot of you have learned before. We will do that, but in the next module, we'll practice that. When you write complete electric configuration, you need everything listed down. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Again, notice it's going from 4s to 3d. And write the complete electric configuration of iodine. Iodine, again, capital I, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10,